Hello everyone, welcome to the next video of our lab on DMA scatter-gathered mode. So in the previous video, we discussed about the theory behind the DMA scatter-gathered mode, and we discussed how to set up the MM to S and S to MM channel along with the transfer descriptor in the DMA scatter-gather mode. Now we are going to discuss the example where we are going to set up the DMA scatter-gathered mode for only one transfer of packet, and we'll compare the performance with the simple DMA. So here we are considering the matrix multiplication example. It's a floating point matrix multiplication of size 8 x 8. The IP is developed using the HLS, and then we have the two DMA. One is the simple DMA, and the settings of the simple DMA is same as the before, and the second is the scatter gathered mode DMA. In the scatter gathered mode DMA, we enable the scatter gathered engine, and the rest of the settings are same. So in the scatter gathered DMA, you will have the additional port where you can read the descriptor. In the current setup, this scatter gathered mode is also connected to the ACP port, but you can also use the block RAM or any other memory to store your descriptor. Now, after generating the bit stream, we will now switch to the SDK. So in the SDK, we are going to now compare the performance of the 8 x 8 matrix multiplication in the processor, then in the simple DMA, and then with the scatter gathered mode of DMA. So this is the main function where we are doing the, this function is same as our previous lab function, where we compare the matrix multiplication in the processor and matrix multiplication in the DMA using the simple transfer. So we'll quickly look at this function, matrix multiplication DMA. So in the matrix multiplication DMA function, we are first defining our internal variable to store the input matrix A, B, and this is the output of the software implementation of the matrix multiplication. And this is the output of the hardware implementation of the matrix multiplication in the FPGA. Now for the DMA, we need to serialize the input. So this is the DMA input is used. So the size is matrix size into 2, because there are 2 matrices we need to send as an input to the IP, and the output is only 1 matrix. So our matrix size is this one. Then we configure the DMA as we did in the previous one. Then we run the experiment multiple times to get the average time of the matrix multiplication. We generate the input. For this input, we perform the matrix multiplication in the processor. This is the matrix benchmark function, which we have already discussed in the previous lab. And we'll find out the time required for the matrix multiplication in the processor. Then for the DMA, we need to serialize the input. So we'll use the DMA input as a vector, and the input A and B, which are in the matrix form, we will serialize it inside the common input DMA input. Then via simple transfer, we will pass the DMA input to the DMA. So DMA will forward it to our matrix multiplication IP, and the output of our IP will be received by the DMA. Then we will poll the DMA to see that whether the transfer is completed or not. After that time, we'll close our timer so that we know the execution time. Then we, from the serial output, we form the matrix of the received data from the IP, and we compare the output of the IP with the output of the software implementation. So this is the how we compared the performance of the simple DMA with the processor. The corresponding benchmark function is same as the HLS function, which we have already discussed multiple times. Now, our focus of this lab is the scatter gathered mode DMA. Now in the scatter gathered mode DMA, as we discussed, there are multiple steps. The first step is to configure the DMA, then set up the MM to S channel, S to MM channel, then create a descriptor for the MM to S, and create the descriptor for the S to MM. Send the descriptor to the DMA, wait for the DMA to complete the descriptor, and finish and free the descriptor. So these are the steps we need to do. Now in the scatter gathered mode DMA, again, we will write a separate function. So in the scatter gathered mode DMA, again, as usual, we will define the corresponding internal variable to store the matrix input and output matrix, software output as well as the hardware output. Okay, so we'll have the A, B, and C. This is same as our previous case. Now here we will configure our DMA in the which is in the hardware in the scatter gathered mode. We will verify whether the DMA is in the scatter gathered mode or not, just for the verification purpose. Then we will write a function to set up the MM to S and write a function to set up the S to MM. Okay, so now we will have a look at this function, which will set up the MM to S and S to MM. So we'll go to the TX setup function. So in the TX setup function, again, first thing is that we are going to have the internal structure, which will have all the value, entire information of our DMA instance and the different descriptor, like what is the start descriptor, what is the end descriptor, how many descriptor is there, all the information is there in this structure. Then we'll have this BD template to initialize all the descriptor with some known value. The first thing is that using the DMA instance, we will get the current status of the all the values of the in the structure. For example, the DMA base address we will get from here, in addition to the other information about the DMA. Then since we are not going to we are not going to use the interrupt, we are going to disable the corresponding interrupt bits. So basically we are writing into the DMA control register and we are going to disable the 3 bits corresponding to the 3 interrupts. Then in this case, we are going to generate only one the buffer descriptor. So using the BD ring create, we have already defined what is the memory location where we want to create a buffer descriptor. This is the physical address, this is a virtual address. In our case, both are same. Minimum alignment is 40 hexadecimal 40 bytes, and the number of descriptors we need to create is 1. So in this case, now you can see that this function will create a buffer descriptor, and the address of the buffer descriptor will be updated inside this structure. So now in this structure, we know that where is our buffer descriptor is created, what is the address of that. Now, also in this buffer descriptor, we know that it is, in our case, it's a 16 bytes of 16 32 bits elements buffer descriptor, and out of which the first 2 locations are the pointer to the next buffer descriptor. In our case, since we have one buffer descriptor only, so the pointer to the next buffer descriptor is the same address. So this function will make sure that in the buffer descriptor, the first 2 values are initialized with the address of the buffer descriptor. Now for the rest of the 14 32-bit values, we want to initialize with some 0. So we will use this BD clear 1, which will create a BD template for the buffer descriptor with all the initial values initialized to 0 except the first 2 values. And this clone function will copy this BD template in all the buffer descriptor. In our case, it is only one buffer descriptor, but it will copy in all the buffer descriptor. So after this one, we are going to set the RS bit in the DMA to start. So in this case, we are asking the DMA to start the operation, but we know that the DMA will not fetch the buffer descriptor until we write the address of the tell descriptor in the DMA register. So we have DMA is we have the DMA is running, but it is not yet fetching the buffer descriptor. So this is the process for setting the MM2S channel. Now the next process is after the RX TX setup, we need to repeat the same process for the S2MM, that is the RX setup. So in the RX setup also, we'll do the same thing. We'll have, using the DMA instance, we have our own structure. We will disable the interrupt. Then we'll create one buffer descriptor. Then we'll initialize it with the some known value, zero value except the first two element, and then we'll do this. We'll start the S2MM channel of the DMA. So by setting the RS bit to 1. So this is the first step we have done, where we have set up the S2MM and the M2MM, S2MM and MM2S channels. Now, next thing we need to do is that we need to create the buffer descriptor. So what we are going to do is that we are going to again run the experiment EXPT number of times. So to get the average time, here we are going to generate the random input, and then we are going to perform the operation in the PS so that we get the benchmark output for comparison. The next thing we are going to do is to serialize the input for the DMA using the serialization function. Then what we are going to do is that we need to now create a buffer descriptor. So we know that we have already created one buffer descriptor, which all the values are initialized to 0 except the first two values, which are pointed to the next buffer descriptor. So we need to write the address of the our input for the MM2S and address of the output in the S2MM buffer descriptor. Also, we need to inform the we need to write the length of the data to be transferred inside the buffer descriptor. So by using the BD ring allocate function, we are going to get the address of the buffer descriptor. So this is the pointer to the buffer descriptor. We will get it. Then in that buffer descriptor, you can see that this is the address at which I want my DMA to receive the write the received data from the IP. So I'll set the buffer address in the buffer descriptor to this value, which is nothing but the some memory location. So at this memory location, I'll receive the data. Using this one, I'm going to write into the particular field in the buffer descriptor. Then in the control register of the buffer descriptor, I'm going to set the length. So here you can see that at the receiver, I'm going to receive one matrix. So that's why the size is this one. After this one, then inside the S2MM buffer descriptor, we don't need to set the start of frame and end of frame bit. So we are initialize them to 0. And then this is optional step to set the ID to the buffer descriptor. We can skip this one. Now inside the memory, where at the location at which I'm going to receive the output, I'm cleaning it. I'm initialize them to 0 just for the purpose of verification. Now same process I need to do it for that MM2S buffer descriptor. Again here I'll allocate the one buffer descriptor. This is the address of the buffer descriptor where I'll get it. Then I'll set the buffer address to the DMA input, because this is the input DMA should read and pass it to my IP. Then the length here, since I'm sending the two matrices, so you can see that the length is appropriately defined. After that, I am since we are sending only one buffer descriptor, so I'm setting the start of the frame and end of the frame bit to 1 for that buffer descriptor, and I'm setting the ID appropriately. Again, this is the optional step. So now we have created the buffer descriptor. Next step is that we need to give this buffer descriptor or pass this buffer descriptor to DMA. And how this is done? This is by writing the tell descriptor address inside the DMA register. So you can see that we are using the BDA ring to hardware, and now in this case we will write the tell descriptor address to the DMA, so that DMA will start fetching the corresponding buffer descriptor. So this is the where the DMA will actually start working or fetching the buffer descriptor and come up reading the data and to passing it to the IP, and output of the IP will be taken by the DMA and written at the appropriate address. Now, whether the DMA has completed the operation or not, what we can do is that we can read the status register of that DMA channel. And in that status register, we know that the last bit indicates whether the DMA operation is complete or not. So here you can see that I'm going to check the last bit. As long as it is 0, I'll be in the while loop. When it becomes 1, the corresponding buffer descriptor has been completed. And the same process I'll repeat for the S2MM channel. Then I'll receive the buffer descriptor from the hardware. So that buffer descriptor will move from the hardware to the post hardware state. Then I'll free those buffer descriptors. So now buffer descriptor will be free and we can reuse it later. And then I'll calculate the time. I will convert the output of the DMA into the appropriate matrix, and I'll compare the output of the hardware with the output of the software. So this is how we can use the DMA in the scatter gathered mode. So we need to note that here we are only using the one packet. So the operation is not significantly different than the simple DMA. It is just that a DMA is reading the buffer descriptor. It will know that there is one transfer to be performed in the MM to S and another transfer in the S to MM, and the DMA will write the data back to the appropriate memory location. So now we will analyze the performance of this code, and we'll see which one works faster. So in the beginning, I'll run the entire code once so that we'll get the comparison between the two TMA. So now you can see that the for the 8x8 matrix multiplication, PS processor took 25 microsecond, simple DMA took 7.63 microsecond, while the scatter gathered mode DMA took only 7.05 microsecond. Now we will go step by step to understand what is happening in each step of the this code. Okay, so let's skip the first simple DMA. Will be here. So now you can see that we are in the SGDMA function. So in the SGDMA function, first step is that, okay, it will do the DMA configuration. So now we'll go to the TX setup function. So in the TF setup function, so we are in the first is we are going to create an internal structure. So you can see the TX ring pointer. In the beginning, it is initialized with all 0. It has the value, you can see that the base address of the corresponding IP, whether what is the state, whether the alignment is done, data width, at first address of the buffer descriptor, length of the buffer descriptors, separation between the two buffer descriptor, what is the state of the buffer descriptor, how many buffer descriptor are in the free, pre-hardware, hardware, and post-hardware state, total number of buffer descriptor, whether the cyclic mode is enabled or not. All this information we will copy it for a particular DMA. So we are here. So you can see that the corresponding information has been copied. So this is the maximum transfer can be done using the one buffer descriptor. It is 2 to the power 26. And rest of the, you can see that this is the DMA base address. Now, what we are going to do is that we are going to create a one buffer descriptor with the base address, this one, and you will see that now this values will be updated inside this ring pointer. So you can see that we are created the one buffer descriptor at this address. The length of the buffer descriptor is also updated, and the corresponding addresses are also updated here. And you can see that the buffer descriptor in the free state. Now we are going to create a template, and now you can see that at this point only the buffer descriptor is created at that memory location. So you can see that the buffer descriptor is created at this location, and the first two locations of the buffer descriptor are initialized with the pointer to the next buffer descriptor. But here it's just one buffer descriptor, so it's the same address is given. And the rest of the addresses are right now initialized to 0, but for the sake of demonstration, I'll just update it to some random value. Okay, so now you will see that after I'll create a BD template, okay, with all 0 BD except the first two elements are not initialized, because those first two elements we need to protect them. And now it will clone the particular this BD template in that buffer descriptor, and now you will see that this value and this value is reset to 0. So you can see that this value and this values are reset to 0. So it has created our dummy buffer descriptor. Now we are going to start the corresponding RS bit of the DMA. So here now, if I see, I can read the control register of the DMA. So it is, you can see that it is 10. The first bit is 0, the RS bit is 0, and the second bit is reserved bit, and it has been set to 1. So that's why the value is 0. Now, after you execute this function, this value should change to 3. So let's check it now. So you can see that the RS bit is set to 1. So the corresponding register, control register, has changed to the 3. So same process will repeat it for the RX setup. I won't go through the details about the RX setup now. So same process will repeat for the RX setup. Okay, so now here we are going to generate the input for every experiment randomly. Then we perform the matrix multiplication in the processor so that we can get the reference output. Okay, so here you can see that we got from the software, we got the reference output. Then we will serialize the input here. Now, what we are going to do is that now we need to update our buffer descriptor. So now if you look at our buffer descriptor, it has only the first two, that is pointer to the next buffer descriptor. Rest of the values are 0. And if you look at our receive buffer descriptor, the receive buffer descriptor address is okay, this is my receive buffer descriptor address. Yeah, so receive buffer descriptor is also not updated. So we need to update it. So we'll start with the receive buffer descriptor. We'll first set the buffer address in the this one. So we want our receive data to be located at this location. So we want our receive data to be at this location. So the address of this location is this one. So 0100130. So this is our location. So we need to set in the descriptor that the address where the data should be stored. So we'll see that this address will be written in the buffer descriptor. So you can see that the address has been written. Now we are going to update the control register of the buffer descriptor to set the size. So this size is mat size into the mat size. So 8 into 8, 64 into 4, because it's a float, so 32, so 256, that corresponds to hex 100. So we will see that that number is written here in the control register. Then the start of frame, end of frame bits are set to 0 in the control register, so you will not see any change. And the ID is the address of this one, so you will see that the ID has been updated. Now, if you look at this address, so that is 0x 3. So now we are going to clear this memory location. So now if you see this, you can see that the entire memory location has been clear with the 0. So here the DMA is going to write the output of the IP. The same process will repeat for the MM to S buffer descriptor, and you will see that the up to this point, the DM, this is the address of the DMA input signal. So if you look at the DMA input, yeah, the DMA input, you can see that this is the address of the DMA input that has been passed to the DMA, and this is the 200 is the total length of the data to be transferred from the memory to the our IP, because there are two matrices. And now we are going to set the start of frame and end of frame bit 1, so you will see that the updation in the status register. Okay, so you can see that the value is changed to C. Okay, so that's why both the bits are set to 1, and then the ID is set to 1. Okay, so now we are going to pass this buffer descriptor to the DMA. So because we are going to write to the tail descriptor of the DMA. So if we look at the address of the tail descriptor, if I remember correctly, it should be the 10. Let me verify it again. Yeah, you can see that the tail descriptor is written as 0. So now we are going to update it. This is the return 0 for the MM to S, and for S to MM, the address of the tail descriptor is 40, and it will also be 0. So now we'll write it into the this one. So let's look at the one for the S to MM. So you can see that the address has been written in case of the S to MM, and now you will see that the address has been written in case of the MM to S. So for 10, you can see that the address has been written, the tail descriptor address. Now we will keep on reading the status register of the 1, and once it is completed, we will send the retrieve the BDs from the hardware. Okay. So run to this one. Now, if you see in the our TX register, the BD is in the hardware process. Now we will retrieve it, and it will change to the post hardware state. So now it has been changed to post hardware. Same process will happen for the S2MM, and then we will change it to the free state. So now if you look at this point, now the BD has been changed to the free one. Okay, so with this we have completed the detailed description of the scatter gathered mode with the one packet. In the next video, we will discuss the scatter gathered mode, where we are going to transfer the multiple packets, and there you will see that the significant gain in performance of the HGDMA with respect to the simple DMA and the processor.